So depending on my personal circumstance, either I will talk about this how causality can be obtained from Tomita Takasaki in my last talk, or I'll talk about QCD and its phases if I get the PDF. The latter, I think, is really new, so it would interest you. I think something new happens. These formal considerations have a strong impact on actual physics. So I'll talk. I raised one was the Raphael Sorkin's experiments, and we found that the Raphael Sorkin was finding causality violation with canonical assumptions about observations, classical of quantum observations. In his case, there were 3 steps. Just a 3-step process, and in the middle step, one is making an observation on some operator, but on an entire space-like surface. So it was mixing. The observations were being carried out globally. That is, so it was being done even in causally separated regions, in particular regions which were space-like, which are time-like related to some portion of this time-like step 2, but the other portion, but it was space-like related to the observation at region 1. So region 3 therefore is space-like related to region 1, but time-like related to region 3, region 2. So in that case, he found that one can transmit information on what has happened in region 1 to region 3, although they were space-like separated. So this is a remarkable experiment. It's coming because of the fact that there was entanglement, basically because of entanglement, and the fact that you are carrying out experiment which is connecting space-like separated observables, and that is going to be the source of the problem, which we will solve later. So again, reminding you, normally we assume that the algebra observables in the region O and this causal complement are commutative. So O prime is the causal complement of O, and the algebra observables in O prime, A O prime, commute with algebra observables in O. And we also often assume that A of O prime consists of all the operators commuting with AO. So it is also AO prime, AO full prime, which is called the half duality. So we will assume it as the need arises. And we would like what we expect a priori, and that's what caused all the trouble, is that there should be states, because O and O prime are space-like separated, there should be states which factorize between observables in O and O prime. So we expect state omega acting on alpha hat times beta hat prime should factorize into omega 1 alpha prime, omega 2 beta prime, omega 1 alpha times omega 2 beta prime. It should factorize, which is statistical independence, which is what happens in the normal measurement theory. This assumption you will see it does not work. So normally you can easily create that thing by taking a wave function, state, like vector state, which is the tensor product of a state localized for alpha times tensor state localized for beta prime. And that will give you the job. So Raphael raised this issue, and one would find that this does not happen. What is the reason this does not happen? Let me go back and tell you why it happened. This trouble arises. Let me see. Yeah. So let me see what the trouble is. In quantum field theory, what is the trouble? These local algebras are all what they call four-dimensional algebras. But the main property of these algebras for our purposes is that if I take all its commitants, A prime, and take the commutant of the commutant, you'll get back the full. If A is a four-dimensional algebra, A double prime is A. Take it as a definition of a four-dimensional algebra. So If you look at the algebra generated by A in the region O and the region O prime, which is completely separated from A, okay, let us see what happens. We also have irreducible representation of AO and AO prime, okay, irreducible. So what does it mean? That the AO, okay, I'm taking the complement, the commutant of the algebra generated by we want this AO, so observables in O, to be irreducibly represented, which means that the center of this AO is a multiple of the identity. Just like Schul's lemma for group theory, this is what we do. Likewise, AO prime, the center will be again multiples of the identity. So they share the multiple of the identity. So if I take the commutant of both of this, which contains the commutant of AO, that consists only of center of identity, and it will also contain AO prime. So the thing that commutes with this will consist of this, which involves center of the center, yeah, multiples of unity. And it will also now take one more commutant of this one. I cannot contain this because I wanted to take one commutator. Right? So it will contain this thing here, the commutator of this, the commutator, the center of this one, commutator, this product will be simply multiples of identity. Okay? When I take prime here, one prime, the thing that commutes with this will always be purely multiples of identity. This is the problem. Because if you take down the double prime, to get the polynomial algebra, which the original one generates, and you have the first prime is giving a multiple of identity, so the second prime will give you all bounded operators on the Hilbert space. Because it is multiple of identity, so everything will compute with it. It's not this, it is all the algebra on a Hilbert space. All the algebra in the Hilbert space is like quantum mechanics. So definitely it has pure states, the standard density matrices, but then it will also mix objects. This states you are writing will go across from O to O prime, because that is how this phenomenon is happening. So you will not be able to factorize the state. Some density matrix which will necessarily be entirely between this and this. Okay. This is the source of the problem. Okay. So here I have written the typology of these algebras. In this case, it is type 1, in like quantum mechanics. So there is no problem in if you do this. That's what we normally do. We will end up by finding all bounded operators on a Hilbert space. Can find density matrices, but they will not separate observables in O and O prime. They will give you mixed states or with non-trivial expectation in O and O prime. Okay? So they will always mixed. There will be some entropy associated with them, and that's the kind of thing that Raphael was finding in this original argument. So this factorization cannot be done. If you look at this factorization is between observables in a region O and the observables in its causal commutant. Then we are looking for states which will factorize. The statement is such factorization cannot be done. You can say right away that it cannot happen, but historically, Raphael found this in trying to Raphael, Luca Bombelli, and who else? I think it was some, well, there were a couple of others in that paper, and they were finding how the black hole space near the horizon is getting entangled with stuff in the interior to get an entropy, and they were finding divergences. The source of the divergence is exactly this. Okay? And now we understand it much better. Yeah. So, I have not used, I have not even used AO. No, I have not used, have I used? I don't think so. Prime. That is Haas duality. But in this argument, I have not used it. I don't think so. Because I have only used the fact that both are factors. That is, the center consists of multiples of identity. So that is all necessary. That is necessary. Even the typology of the algebra is not needed. it will happen. If you do this, you will find that the pure states, all states are entangled. That is hard. Because A of O prime is also supposed to be a factor. So that is the crucial assumption. If you say A of O prime is not a factor, suppose you say that, then this calculation will not work. Okay? So that's what will happen when we go one step further. Okay? But whether failure of Hawk's duality.
So simple what you get. There is a that means that you're looking at the smallest volume and then you go to that.
Yes.
It need not be a factor. The smallest volume and the continuing factors need not be a factor itself.
So
unless you assume the Hawk's duality.
That's what I don't understand. We go back. Okay. So I look containing both. So it contains AO. So it contains all the commitants of AO. Okay. You're saying, yeah, so Hawk's duality may be needed. So I understand. The commutant of AO may contain more things than AO prime. That's what you're saying. But if that is not a factor, the thing is that the commutant of AO must, which is coming here, is maybe larger than this, but it should be a factor.
I agree. But what I'm saying is the smallest volume containing two factors did not be a factor itself.
Maybe not.
Yeah. So you're looking at the component of the joint algebra. So how do you expect that the sample will be?
So I might have to say, you say a little bit think about it, but I might have to say that I'm assuming Hawk's duality in that reason.
So with Hawk's duality, it should be covered. It's not a full duality, right? Fields are different.
I don't know. I don't think so. Because if that were the case, somebody else would have remarked on this. But I don't know for sure, because I did not think about this subtle point. I had assumed that Hawk's duality is always okay.
It fails
internally.
It's not always Hawk's duality.
No, I agree with you. So whether that will affect this, I do not know. So I'll come back to it. I'll try to think about it. Okay. So we are going to avoid it. So I'm going to see how algebraic quantum field theory avoids this. It is but there are a couple of things one should take from here. Let me see what's the best way to go. Okay. So the main thing I had to do to avoid this problem. So, yeah. The main assumption which I will be using, main assumptions are these. The first assumption is there is something called the split property. What is a split property? It is a process of regularization. This is your O. The O prime will be the algebra which comes large. Here, O prime will start with a cone from this black point here on the left and the right. In 3 dimensions, it will be some connected region. But O epsilon prime is split from O prime by a small amount. So you split the larger diamond little bit, no matter how small, but a finite distance from here. That's your cutoff. If you like, we are algebraic people are introducing a scale cutoff, very much like in our ordinary quantum field theory. If you do that, there are actually very strong arguments that you can do something great, and this regularization, along with certain further properties which I will describe to you, will solve the problem, can solve the problem. So, if you do this, Hmm?
The region above this diamond structure is also O prime epsilon.
O prime
It's not
epsilon,
just-
yes.
it's not
O prime epsilon, yeah. O prime epsilon is smaller than O epsilon. Okay. You should remember that because I have made, sorry, O, O prime epsilon is this one, yeah, sure. It will be like this. Okay. So O epsilon is larger, so a O epsilon prime will contain O prime. Okay. Because,
That's not what I asked. What I asked was the O epsilon is diamond,
yeah,
and anything that is not the diamond part region is the O prime.
yes.
It's not just those.
Uh, this,
What you are marking is a diagram as O prime epsilon. That is not just O prime. Then the top and the bottom will be O prime.
wait a minute. This I'm not sure because O epsilon, O prime, it has to be causal, no? So even let me see. You can have light rays, it can go at angles. Okay. So I start any point here, you can have a light ray going that way or this way. So they will not be in the causal complement O prime epsilon. So you want the causal complement of O, this O. Okay. So O prime itself is this and this, but you're asking why do they take any region outside of this causal diamond? That won't be in the causal complement.
What is the definition? Is it the complement, causal complement of completion of O epsilon or what?
O epsilon, there is no question of completion. You take O, it's a open set of this causal diamond. Okay. Now you ask what is the causal complement of O? Causal complement of O normally is the Riddler wedge that you get on both sides. Now, if you make O a little bit bigger, the causal complement will still be the Riddler wedge. Now, what I am listening to you is can it be larger? Maybe every other region here that's not true because you can take light rays going from here in all kinds of directions. Okay? So the Lorentzian geometry is not what you're suggesting, I think. Okay? So this is quite important. I mean, when you are discussing causality, so it will have the topology of a Rinder wedge. O prime epsilon, this region will be some Riddler wedge which will be contained in your original Riddler wedge, okay, but little bit inside. So you take a Riddler wedge inside the original one. Okay. So what I will show you that in this case, there is a some property called the split property, uh, which uh, which enables you to find a state. Okay. One on O, observables in O, the other is on observables in O epsilon prime, which factor is. Okay. So this is quite remarkable, but there is no such thing you can do in O and O prime, but in O and O prime epsilon you can do this. Okay. So you have this case, but even more remarkably, which I think is quite astonishing, you can make local operations which will change this omega 1 to any state you like in O without affecting what is happening here. So you can make local operations in O. It should not affect what's happening here, but it will change this into anything else. Likewise, you can do local operations here, change omega 2 to anything that you please without affecting omega 1. Okay. All this is coming because there is split from this little thing I have done by separating the two regions, plus a very important result, which I will illustrate, which is called Murray-Forneyman equivalence of projectors. Okay. This is such a new equivalence class on projectors, which Murray and Forneyman described, is very easy to understand. I'll show you examples. It happen only in infinite dimensions, and it so happens that in these type 3 algebras, this equivalence of projectors is extremely important, but quite easy to understand what they are telling and how they can be used to manipulate states in the two regions. So, if you do this activity with the split property, you will not see any entanglement because you can remove somebody else can go and change the state locally without affecting anything outside the world. Okay? So that's what I want to show you. Okay. Okay. So what is a split property?
What you have shown here is there exists product space between O and O prime epsilon.
O prime epsilon, yeah.
Yeah, but that does not guarantee that there will be products between O and O prime.
No, there is no such thing. There is no such thing.
Yeah.
That problem cannot be solved because it diverges.
Yeah, maybe, the only common thing between what happens O and the talking.
Yes. That's it. Okay. So this splitting, this regularization is very important. And the regularization, if you want to call it regularization, has very strong mathematical consequences. The second mathematical consequence, mathematical result I am using is the so is this statement which I made about the equivalence of projectiles, which I'll show you in a minute. Okay? But before I go on, let me make a few more remarks. Okay? The first remark is that these local algebras have no finite dimensional projector whatsoever. There is none. That means that the trace, so every eigenvalue of any operator in this algebra is infinitely degenerate. Okay? So no matter what what operator you take, it is infinitely degenerate. The spectrum is infinitely degenerate. At each point of the spectrum, it is infinitely degenerate. So one cannot take trace of this operator. There is no trace class operator. So you cannot write a microcanonical ensemble for any operator in this algebra. There is no such thing. Okay? So this is a very strong statement. Okay? The second statement, which you will see in a minute, is that although this is correct, nevertheless, we can find density matrices. We will find it. But these density matrices are not in the original algebra. Normally, if you do finite dimensional matrices, the density matrix is some matrix in the algebra of invariant matrices. Okay. Here, these density matrices are not in the original algebra. But nevertheless, every one of these density, but they can be evaluated on your you can take a trace of the operators in your algebra with these density matrices, which may even be finite dimensional. For example, it may be a vacuum state. So you can take the vacuum expectation value operators in AO, no problem. But the theorem says that every one of these density matrices is a vector state. That means you take any density matrix and evaluate it on an operator. There is some operator in the Hilbert space, some wave function there, some vector state in the Hilbert space, such that this is the expectation value of this state. Okay? I'll show you why this is very important. But notice that the corollary is that the density matrix you are writing, psi omega, is a rank 1 operator. If you take a trace, you get 1. Okay? Because these size are normalized. So it cannot be in algebra, because if it were in algebra, it will be infinite dimensional. But this is not. So this density matrix I am writing is not in the algebra. It's coming from outside. Okay? It is not in the algebra at all. If you like, this is another reason why you can expect entanglement all the time. The entanglement is the general property of these algebras. Okay. So here I am going to get a little bit technical. Okay. I apologize for this. I think you will get confused, but let me go slowly. So the theorem these people proved, I don't know where this theorem originates from. The split property, I saw it first in the papers of Sergio Doppler, Hagen Roberts, but I don't know whether it predates, but it certainly is in the book of Hart, and it is discussed very carefully. The statement is that the split property, which is he said about nuclear property and so on, something about density of matrices not growing too fast at high energies. That's the crucial point. So the density of space of your Hamiltonian does not grow too fast at infinity. Then the split property exists. And what it is saying is that when you split O into a larger region O epsilon, look at the algebras in these two regions. AO is actually contained here. This is one of the original assumptions. But the theorem says, the proof says that in between you can insert all bounded operators in the Hilbert space. So you can already see that the Hilbert space we are talking about has very straight properties. So how do I do it? So the claim is that there is split. This is the split property. Bounded operators are splitting AO and AO epsilon. So how am I doing it? So here you please be patient and on what I will do. I may myself get confused. What you do is you represent these algebras on tensor product of the Hilbert space with itself. So you take H cross H. Then AO you embed in this H cross H as AO cross identity. This is a representation of this AO on H cross H. Of course, it is not reducible. It is a large tensor, but you embed like that. This is certainly contained in all bounded operators cross one. Okay. The all bounded operators swallow all operators in the Hilbert space. So this is certainly contained in this. This in turn is contained in all bounded operators, but I put AO epsilon here. So notice the way I am positioning AO epsilon. So this inclusions make sure that the first entry here and the last entry here, first entry here is contained here because AO cross one is contained in this thing also. Okay. So first entry here is again contained here because AO is contained in BH, identity is contained in AO epsilon. So it is certainly contained here. Which is also true, should be important later, that the tensor product of all the bounded operators with AO epsilon is still of type 3-1. The typology does not change if you tensor type 3-1 with anything. Okay. So the algebra of this is the largest index always dominates in the tensor product. So this is also of type 3-1. So what happens to the commutators? Okay. Can I also position it nicely? So I'm going to now position the commutator of AO epsilon as identity cross AO epsilon. I'm going to read this line backwards. Okay. So I'm going to take identity cross AO epsilon and I put it instead of this part here, first line, I put it in all the bounded identity cross all bounded operators, which is certainly contained here. Then in the last line, I put A of O prime. So, but this sequence here, you can see that this thing here is contained in the last one because this AO prime certainly contains one and AO epsilon prime is certainly contained in BH. Then you may ask, in this inclusion, does this AO epsilon prime commute with this line here? This is supposed to be AO epsilon. So this thing here should commute with this. Because this is a cosmic complement of this one. And it is because AO epsilon is appearing on the right side and AO epsilon is, they will commute nicely, no problem. This will also commute with this. So this sequence of inclusions is certainly allowed. Now, why am I doing this? To remember this, unless you are doing these calculations, again and again is confusing, but I will use it in a good way, quickly, to show you how to do manipulation. The manipulation is done. Suppose you give me a state on AO. I want to change the state in AO. So you give me a state omega on AO. So, so the element I am taking will be some element alpha tilde, which I call as alpha tilde I am writing because here it is will be some alpha hat here, tensor 1. Okay. So this is simply the representative of alpha tilde on this tensor product. And I am now in this infinite dimensional setting. So this omega is on this infinite dimensional algebra. So I know that there is some vector space psi, which the expectation will be here is going some vector space time psi on alpha. Okay. So this psi is going to be psi cross 1. Something, okay, because one is necessary because here there is a 1 here to check it out, we put this 1 here. So it will be some state like this, where this guy is living in the first edge and this one is going for a ride. Notice that this thing here, this density matrix I am writing is infinite dimensional. So because it's all this one, this is not, this looks like rank 1, but this 1 is not of rank 1. If you take a trace, you will get infinity. And this state here, they are called E. Is E side is a rank 1, tensor 1. And this thing here is living in bounded operators called 1. Okay. So it is very important that the density matrix I am writing, the psi I am writing here, the corresponding density matrix is infinite dimensional and it is living in this. It is something associated to this type 3-1 algebra because the alpha tilde is also of type 3-1. In the standard way. Here I have only taken expectation values. There is no trace. The trace is infinite of this operator is infinite. Partial trace you can take. The partial trace will be 1 here. Right? But I am not doing that. Yes, it is 1 for the first part. But here the trace of this operator is infinite. Because this 1 is a huge matrix with 1, 1, 1 along the diagonal. Right? So it will be infinite. So I will not take a trace of that. But when you take the expectation value here, what will happen? I am taking the expectation value of psi cross 1. Okay. So let me see. So you get this expectation value psi, then what will happen? Yeah, let's say this is the definition of the expectation value. So omega on alpha tilde will be given as the see the point is alpha hat is an operator which is where is alpha tilde is an operator one cross, right? So alpha hat I'm taking the matrix element of this thing here is living here. This thing is living here. Okay? So I'm taking the expectation value of alpha tilde in this state. Okay? Expectation value of alpha tilde in this vector and this. These are the problems which taking traces. Is there a problem? I don't know. Do it make sense in this equation? No, it's okay. This is a definition. Okay. So omega, I'm defining omega is a state on this operator, and I define omega to be this. That's well defined. Now I take this side and I construct a new operator, which is not a trace class operator because of the 1, and I write it as E side cross 1. So it's not a density matrix. Absolutely. So that was my temporary confusion. Of course, this construction is highly non-unique because nobody told me that this psi I am writing is unique. Okay? There are many states which will give me the same expectation value. Okay. The corresponding operator, this is more interesting. The corresponding operator which I am writing is living in BH cross I. Okay. BH is all bounded operators cross I. But BH cross I embedded in this type 3-1 fundamental algebra. So this algebra is type 3-1. So because it's being type 3-1, it is what they call Murray Forneman equivalent to something. In fact, it is Murray Forneman equivalent to any projector. So that's what I'm going to show you. So this is my statement. And so the theorem which Murray Forneman proved, which is given in which is given in the review of Fredenhagen, is that any projector in these algebras is what Murray Forneman called as partially isometric to identity cross identity. Any projector. Okay? That means any two projectors, this is an equivalence relation. So any two projectors are equivalent. You can take any projector and you can make a Murray Forneman equivalent transformation and you can get the second projector. So what is the equivalence transformation? What is the equivalence relation? The theorem is quite easy to understand. I'll give you an example. Is that any projector can be written in terms of a W, infinite dimensional, so that this projector E I start from is W star, whereas identity cross identity is W star W. Okay. So if you write two projectors E prime E1 and E2, there will be a W, so that E1 is W star, E2 is W star W. They go back and forth. Okay. So this is, and if you have several of them, you may have W1, W2, and so on. And you prove that this is an equivalent relation. Okay. That's quite easy to show. If E1 is equal to E2, E2 is equal to E3, then E1 is equal to E3 and so on. That is easy to prove. This is called the Murray Forneman equivalence. And one consequence here, so I take my projector E, with which I started the game. I took omega, it gave an expectation value in the state side. And from there, I constructed the projection operator E, which was infinite dimensional, and that has this property. And you see that from this equation, if I multiply this E by W star on the left, it is W star, right? Because the W star W is 1. If I multiply E by W on the left, right, is again W, is W. Okay. So this projector, these things fulfill this property. Okay. I'm going to use this to show you how to change any state to any other state. You may want an example. This cannot happen in finite dimensions. I'll give you an example. Take a Hilbert space with an orthonormal basis. Call them basis as En, and it's an orthonormal. So En with M is delta Nm. And I'll show you a partial isometry, this kind of partial isometry. So what do? I arrange the basis like this in a column here. So E0, E1, E2 goes up. Here I have arranged the same thing. Now I define an operator W, which doubles the number. So E0 goes to E0 and a W. So actually on W, E0 I get E0. On E1 I get E2. On E2 I get E4. And E3 I get E6 and so on. And what is W star? W star is adjoint of this. Here, if go back to 0, but since E1 is not in the image of W, it is 0 here. It's not given thing. When you take the adjoint, by standard definition of adjoint, it gives 0 here. And so good. All the elements in this column, W star will give 0. All the elements with odd index, it will give 0. On odd even index, which is W star will give 1. Okay. I go with W here and come back with W star, I get 1 on all the even subspace. And all the subspace plus odd subspace, I get 0. Okay. So let us see how this looks like. Yeah. So this is an example of a partial isometry. So the one way W, I apply W star to W, it is, first I apply W, then I apply W star on the image of W, it is 1. So it is identity W, W star W is identity on this Hilbert space, but W star, the other way around, is a projector on the subspace of even indices of the basis of the Hilbert space. Okay? So one is a projector, the other is identity, and these two are Murray-Farman equivalent. Okay? So this is a very simple example of how this kind of phenomenon can and does happen in infinite dimensions. This is the crucial thing that I want to use.
How did the
I'll show you. On a basis, it's enough to show it on a basis. Take E0. First I apply W. Take E0. And then I apply W star on the image. I get back E0. I take E1. Apply W first. I get E2. I apply W star on the image. I get back the same E1. So W star W is 1 on E1. Right? I go back and forth. But if I take an odd thing, there is nothing. Odd, this W is 0 on odd thing, right? I'm saying the image, not a W star. Image of W does not contain the odd things here. So if W is going to be densely defined, you apply adjoint operator on the to define what's happening on the image, you get 0 on the odd things. You will get nothing. So this is an example of one way identity. The other way you don't get, you get 0. Get a projector. Okay. W star will be a projector on the even subspace and 0 on the orthogonal complement. Okay. So this is a very simple example. So now I go back. I remind you that from the original state psi, I constructed this E. Okay. E was psi cross 1. Okay. Psi is a finite dimensional projector. Is living in BH. Okay. But yes, E psi cross E identity is E is living in an infinite dimensional Hilbert space. Okay. So I want to manipulate this E. Okay. So the E I wrote down, which I wrote down earlier, is partially isometric to identity cross identity by the Murray-Farman theorem. They type 3-1 algebras. Okay. E psi is not, but E is. Okay. So it is partially isometric means there is some W, okay, and E will be W star, and identity cross identity will be W star W. Okay. There exists such a W. Do I need to find it? For the calculation I'm going to do, no. Only thing you have to remember is that E came from the state omega you chose on AO. Okay? You picked a state and you say, I want this expectation value on AO. So I find the E and I keep going. I don't need the explicit formula. So I want to write it in some cases, you can do it. Okay? In some cases, this is where this business of Kunz algebras come. I will not go into it because anyway, I have no time. And yeah. So let me go back here. From these equations, you see that W star acting on E is W star. W acting on the right of E is W. From this equation. Because of the fact that these two equations, I got this. Ah. You are asking why BH tensor type 3-1 is type 3-1. That's what you are asking. Okay. So, it's not obvious at all. So I searched when I was trying to study it. search the literature on the reduction of tensor products of this fundamental algebras, and there are papers, Hagerup. I did not go through them, but I gathered from learning them that when you have a tensor product of two of these algebras, the thing is that both, when you are taking the tensor product, they share an identity. And when you take the tensor product, what remains, and of course, the tensor product is in the Fortnite says you take the tensor product and you take the double commutator, okay? Always. Okay? So they still, from what I understand, still remain factors. So these are fundamental algebras with factor again 1. Okay? Then there is a proof that the subscript higher always wins. Okay? So that is the result I observed. Okay? So I think he said those are associative. Tensor products are associative. So if you take type A cross type B, B is larger than A, is B again, then you keep going. Okay? So it is associative. So I think this is always correct. Okay? I wish I see to understand these proofs very often for me takes a long time. Okay? And maybe I don't understand it all at the end. It confuses very good.
For me, it's surprising there is that always the higher type.
Yeah, that's a rule. Okay. The problem is that sometimes you need to know the proof to get some other result. Okay. Then you have to go back and check what is happening. Okay. And it can be difficult without some help. And in my case, I have Sasha Pinzul, who knows this stuff, or at least he understands fast. So somehow I can escape. Okay. So what I do, so I have told you that the state omega on the AO region can be is an expectation value which can be recovered from E. Okay. That you have a finite projector which can be embedded in an infinite dimensional projector E, and can be and that from that E I can recover a W. So the local operation I'm going to do is the following. Okay? I will first take this alpha tilde, because alpha hat cross 1, and then I will transfer this activity to define a new state in the original algebra, which I will call phi W. But this is some kind of a preliminary to see what kind of thing can happen. So I take W star alpha tilde W. Okay. Let me see what happens. But W star E is if I multiply alpha tilde and multiply by W star, which is still W star. I just showed you in the previous slide. If I multiply W on the right, on E is still W. So this is equal to this. So this in turn is, I look at the right hand side, and this E is E psi cross 1. Then I write this alpha tilde as alpha tilde alpha hat cross 1. Alpha hat is the original observable in O. Then you have E psi cross 1 and you have W. Then we evaluate it. In the middle line, this says phi psi. So I end up by taking the expectation value of alpha hat in psi side with the bra decay, which I write here. Then I'm left here with the ket vector side. Okay. So that on the right hand side, I left the bra vector side. So I end up by getting psi cross identity again. So what I end up with is W star. How did I do this calculation? Yeah. Yeah. I have this W star, and in the middle, I end up with W star again, because as I told you, it's psi cross I. It's in E, it is W star. And then you have W again. So W, and then you just read off. W star W is 1, W star W is 1. So this. Okay. So W star alpha tilde W is the expectation value you want times identity cross identity. This is the great equation that you are getting by this Murray polynomial equivalence. So I now define a new state phi W. This is a definition of new state phi W on alpha tilde, so alpha hat cross 1. Okay. So the new state I am defining on alpha tilde is phi W. Okay. So new state is obtained by taking the state in the what is it, standing in front by applying W star and W on both sides, written in phi. But that will give you this equation. Okay. Because the W phi W is defined by phi W star whatever inside W, and that gives me this times phi on 1 cross 1. But phi is state, so it's normalized to 1. So that goes away, and this is what you want. You got the answer. So as I warned you, this is by no means an obvious activity, but this is what happens. So that means that by using the partial isometry identities, I change my state in O to anything I want. This is true for any any state you choose in the local region, you can change it by this partial isometry. And I just want to show you one more result. Okay? That this doesn't change what is happening in the causal complement. Nothing happens in O epsilon prime. Why? Because I look again on phi W on identity cross B hat epsilon prime. So remember that these things are put in this H cross H, and the way the operators are living in O epsilon prime, A epsilon prime are this character. They put a W star W on both sides, okay, because phi W has that property. But this W, you remember, was coming from here. W was an operator like BS cross over epsilon. Okay. So it certainly commutes with this operator here. This is the causal combination of this one. So I can pull it out. Then W star W becomes 1. I get phi on identity cross B prime epsilon. But that is whatever you started from, and you have come back to what you want. You have not done anything to the causal complement in the split causal complement. So you have done a local operation to change the state locally and done nothing elsewhere. So you have completely removed the entanglement between the two cases, and the state you are finding, whatever you have on O epsilon prime, you keep. You change the thing, the region you're looking to anything you want. Okay. And I found you the state by local operation because I don't do anything to the causal complement. Okay. And you find that the state is statistically independent. That is factorized. So you can get any, in this way, you can get any two. Give me any two. What is it? Give me any state which on two regions have some expectation value, then I can do local operations in the two places and get anything else you want. So this is a very remarkable property, and the epsilon band is important. If you remove it, the whole thing will fall. Okay. So the epsilon band is what is causing the, I think, very remarkable result. So I got a lot of things here. Okay. Now, so the issue that I want to raise is, with this, have I resolved Raphael's problem? Okay. It depends. Raphael problem will be now resolved because Raphael looked at cases where a region and its causal complement were touching. Okay. You remember that he was doing experiments on a whole space-like surface, and the causal complement was touching the original one. You split it a little bit, the problem will go away. So let me conclude this lecture by showing another very remarkable thing. I can go into what Raphael thing did and what um, the Schuster, the group in Schuster, Wirtz and so forth did on measurements, they also come to similar conclusions. They actually make more exhaustive analysis. Because of time constraint, I will not do it. Okay. Okay. So, uh, so I want to finish off by saying another mind-boggling result to me, which I found out maybe a few months ago. It's well known to people who do this activity, but to me it came rather late. And this is the following. Uh, First, we wrote a paper on this, that there is no way you can measure a non-commutative algebra. There is nothing you can do. Why? Because they have inner automorphisms. So unless you have some comparison things, let's say, suppose I tell you to measure third component of angular momentum. But how does the system know which is third component? It just has no axis which is carrying around. Okay. So what I call third component, you may call first component. How do I know? Or some other thing. There's no way because algebraically I can make inner automorphisms and without changing any algebraic relation. So all I am given are algebraic relations. So what do you do? You can say that I have a measuring apparatus, a frame with which, but question, is the frame also not quantum? Okay. If it is quantum, it is subject to the same rules. Okay. If it is subject to the same rules, there is the same uncertainty there. So what do? It's an infinite regression and you are stuck. Okay. So how do I remove the infinite regression? Cannot be removed by keeping to the quantum operators which are non-commutative, in my opinion. Somehow a commutative algebra must be emergent from the non-commutative algebra. How it does, we can argue. I think there are many things to be understood there. But within the standard measurement theory, you cannot do it. People saying that I measure something, you can't do it unless they bring in class. They have what is called local operations and classical communication. That is not quantum, it is classical. You should not, if you're a purist, you should stick to quantum mechanics and see how we get answers from quantum mechanics. That will be the deeper thing, in my opinion. But so, what is the theorem I want to tell you? It is related to this theorem. This problem I told you that if you take a state rho density matrix and I measure an operator A hat, okay, then as I told you, if you take A hat and make a unitary transformation on A hat, where the unitary operator comes from the local algebra, algebraically you will not be able to tell. Okay. Algebraically, all operators are undergoing this unitary transformation. Algebraic relations will be maintained. You cannot tell. Okay. So now consider what happens if I take the expectation value of A hat in rho, expectation value of unitary transform thing in rho. Okay. These two things are related by transforming the rho. Okay. So rho becomes U inverse rho U by the dual transformation. Okay. So saying that I am measuring A hat in this state rho is equal to saying that I have changed the states to this new one and looking at the original A hat. So the changing the operator algebra by inner unitary transformations is equivalent to creating an orbit in the space of states. So what is this orbit? What are the states again? There's this context. There's a very remarkable theorem proved by Kohn and Stroman. A really remarkable theorem which shows that they should actually forget about all this. This is very interesting. Yes, it is cyclic property of the state.
On the left hand side, we have the property like this.
A hat is not fixed. Suppose you change A hat. So by duality, there is an action on the set of states. So this is a dual action I am writing. Okay. Now the statement of, forget about this, some of the remarks are referring to Raphael, how this impacts on Raphael, but let me not go into it. Let me look at this orbit. It just the theorem was proved by Kohn and Stormer that in the local algebras of type 3-1, forget about the second thing here, the orbit of any state under these unitaries is dense in the space of states. That is, you can get by these inner transformations of the density of states, you can bring any state into arbitrarily close to any other state, the algebra, and you can't tell the difference. So, this is, if you like, a statement that you can make no measurement internally to type 3-1. They say it. They say it casually that therefore you can't measure anything. Then they go on. This is a very remarkable theorem, and I don't know what are the implications of this theorem, but it's a theorem. They prove it. They prove that this is a property. If there is such a property, it's a type 3-1, and conversely, type 3-1 has this property. I think that conceptually this is a very important theorem, and the implication of this theorem has not been discussed in the literature. That's what I told. I wrote these notes apropos of Raphael's calculation. Okay? So that O prime is coming from what Raphael was doing in the final experiment. But never mind that. Okay? Because I don't have, it's already 3:10 and I don't want to get into that. So I would say that there are many issues to be settled, and it is worth a thought to figure out what is happening. So let me stop here. Next time, if there is time, if my PDF is ready, I'll talk about phases of QCD as a seminar. If my PDF is not ready, then I will show you how the Tomita Takesaki also gives anti-commutation, how it gives spin statistics theorem. That's also very worthwhile, and it is due to some work by Araki. Whatever. He discovered something called cell-dual car algebras, cell-dual canonical anti-commutation relation algebras. I'll tell you what they are. They're quite simple, but they have remarkable consequences, especially in lattice systems. They give new invariance of lattice systems. So my friend Andres used to find Z2 invariance in during phase transitions in some infinite dimensional lattice system. So I'll talk about it. So one or the other, then I'll stop my course lecture. Okay, I think I'll stop here. So I would say that the things you have to really remember, which is very worthwhile, are this fact that projectors in these algebras are always, any two projectors are for Murray-Fortnightman equivalent. Any two projectors are Murray-Fortnightman equivalent, and they're related by these W's. Okay, W's are these partial isometrics. They are not unitary. On one side, they will give one projector, on the other side, they will give the other projector. So they are not unitary, but they are partially, what they call partially isometric. This is something that one should remember, because I think it is a very remarkable research that they presented, and it has all these consequences in quantum information.